Welcome, everybody. I'm Ivan Novick,
Hi, this is Venkatesh Raghavan. I'm a product lead for Greenplum.
and today we're going to introduce Greenplum 7.2, which just released this Friday on June 21st. So let's get started. All right. Before we get into the 7.2 release, just give you a recap on the journey we've been on. And Venky and I have both been on the journey along with a whole number of our colleagues for a long time. But Greenplum started back in 2003. Some of the key highlights were the introduction of our in-database machine learning based on Apache Madlib or based on Madlib in 2011. We integrated geospatial processing back in 2013, introduced our parallel query optimizer, GP Orca, back in 2015. We've been doing the Postgres integration, so we're now all the way up to Postgres version 12. And we also did a huge vSphere and VCF integration starting in 2021 when we were acquired into VMware. And Greenplum 7 came out last year, which has VectorDB, pgvector, and some AI capability. And then the new DR based on write-ahead logs this year. So that's just a super high level timeline. But in addition to that, just level setting where we are with the product, we do sustain a very enterprise friendly release cadence. So Greenplum 5 is still in support based on version 5.30. Greenplum 6 is still being actively maintained and developed, and there's no set end of support date for it yet. We're continuing to do patches and some backporting of interesting features. And then active innovation is being done on Greenplum version 7 right now, and not even any visibility to the end of support date for version 7. So with that being said, just put one slide to recap all the new innovation that was put into GP version 7, which released last September, October. I'm not going to be able to cover all of this, but you can check the other videos where we introduced version 7 of Greenplum. Maybe Venky and I, we can both pick our favorite feature from this list and take a second to mention it. I think maybe my favorite feature here might be, probably disaster recovery, because, for a long time we had the concept that something like a MySQL or an Oracle could do replication between data centers, but big data like Hadoop or Greenplum couldn't really handle that. Now we have the cross data center replication based on write-ahead logs, which is like a real traditional database feature. So we're really bringing traditional database feature towards the petabyte scale databases with Greenplum. That's really the big theme for me. Thank you. What's your favorite feature from?
Uh, what we are seeing in our customers, they have multiple Greenplum instances, and they want to have a parallel way of query processing across these multiple Greenplum instances. So the optimizations that we have done in GP7 with foreign data wrappers and others has been really very performant, and I'm really excited about that. The GP to GP optimization.
GP to GP cross cluster queries. Okay.
Cross
Yeah.
cluster query.
Like I said, we don't have time to cover all of the new things in GP7, but we have previous videos on YouTube you can check for all of the GP7 release announcements. Today, we're here to talk about 7.2 and even touch a bit on what's coming in the future. So this is a bit of the agenda, but I think we can just jump right into it. I think I'm going to cover a couple of the initial topics related to DR and extensions, and then Venky is going to pick up with the query optimizer and the geospatial. So in regards to DR, like I mentioned, we did look into, just so people understand, this is not a cluster to cluster direct connection over the network. It's an archive-based DR. So we are able to achieve RTOs of under an hour, even potentially down to several minutes when in between data centers, when when the infrastructure is right. But what we're looking at here is using an archive. The archive is a middle point, and this really creates stability, because when you're looking at replicating 1,000 segment Greenplum to 1,000 segment Greenplum over a wide area network, and with choppy networks, having this middle tier, which is the where the archive writes to, and the archive could be writing to S3 or to GCP, or you're going to see Azure and Data Domain or even NFS. This creates a very stable way to replicate. So we replicate in real time these write-ahead logs to the middle tier, and then that middle tier is automatically downloaded and replayed, the transaction logs on the recovery cluster. So what's new in 7.2 is we've certified the Azure blob storage. So you can replicate, let's say, from on-prem to Azure and use Azure as your DR environment, which is interesting. It's a little bit different cost structure because you're using DR in the cloud, where you have your, let's say, on-prem data, but DR in the cloud. It's an interesting use case. And we also have certified Dell's Power Protect, or what's also called Data Domain, which is a deduplication storage device, backup device. And that's interesting too, because we actually see data reduction in this scenario, and that gives a good storage efficiency and performance efficiency. So there's a wide range of storage you could use as the middle layer to achieve now DR with Greenplum, and to achieve the basically multi-data center protection for your data. All right, let's go to some of the extensions. So if you're familiar with Greenplum, you know that it is related or derived from the Postgres technology. And so we continue to look at the extensions that the open source world has created for Postgres, and we ingest and extend some of these things onto Greenplum. So pgcron is interesting in that now we have a scheduler to allow you to run queries inside of the database. So a lot of times people were thinking, oh, I have to run a cron tab, but I want to run some scheduled jobs. So now you can schedule jobs in Greenplum. And I'll just fly through this a little bit, right? It's a very similar syntax like you might be familiar with in Linux, where you can set up your cron tab based on when it's going to run, what it's going to do, and what's the command. But this is all scheduled in the database. And in fact, because it's scheduled in the database, you can use SQL to schedule it and to update the functions. You can use regular SQL to go and update these scheduling tables. And you can have lots of different options, like, for example, terminate the job if it doesn't finish after X amount of time, things like that. You can see them in the, I'm not going to go into a full tutorial of it, but you can see some stuff like looking inside the table to see what the jobs are, unscheduling jobs, viewing the job details, all these kinds of things. The other thing I wanted to say is about the scheduling is, in addition to this, and this is a future-looking statement, so I wanted to say it quite carefully, but in addition to this, we are working in R&D on another kind of scheduling, which is something that is more of a outside the database scheduling, which has the potential in the future to allow us to do things like automatically trigger a GP recover seg, or other kind of system level commands. This pgcron is for running SQLs and scheduling SQLs and things you're going to run in the database. But there is some more thought about what we could do from a scheduling point of view, and I'm looking forward to seeing that in the future. As far as the other extension, the ORA FCA. So ORA FCA FCE is a extension for Oracle compatibility. It's built in the open source. We've extended it, which is why it's _ext, because some of our customers want more Oracle extension capability or more Oracle compatibility. So we've added a data type called UTL raw, which is a data type that Oracle has. It's a very low-level data type that helps you avoid, it's like kind of like a binary data type, and it helps avoid conversion errors with string types and stuff like that. So this UTL raw is a new Oracle compatibility function in our version of the Oracle compatibility library, which comes with Greenplum at 7.2. So you can cast to raw, cast to varchar, concatenate, things like that, and allows you to port over from Oracle seamlessly with respect to this kind of data. Okay, let's get into the optimizer hints, Venky.
Hi. As everyone knows, the Greenplum has two optimizer. One is for the transactional workload, which is the Postgres Space Planner, which is the modification of the Postgres optimizer. And the second one is one that is in-house developed GP Orca, which is built for hybrid transactional and analytical workloads. How does the optimizer work? It explores a large search space, comes out with equivalent execution plans, then uses stable statistics and their cardinality estimation model to predict the number of rows at each operation. And then based on that, we can estimate the cost on top of it. And then finally, you pick the lowest plan, the plan with the lowest cost among the search space. That's how both optimizers work in short. Next. But the current solution, so if you always have a scenario in any optimizer where 80% of the time the plans are great, it works amazing. But there are 20% of the time it may not be as optimal as you want. And
Venky, is 80/20 really a real number, or I would think it would be.
I would say it's probably maybe 90/10. But 80/20, if you see in TPCDS, for example, 80% of the plans are super optimal. And then 20% is not optimal, it's suboptimal. That doesn't mean it's really bad. It's not like instead of, say, 2 seconds, it's now taking 3.5 seconds. So
Sure.
that will still be
So,
considered as suboptimal.
so you mean non-perfect, but just for the listeners out there, my experience is people running 20 million queries a day, they might have one or two queries which aren't tuned well, where this might come in. It's not really like 10%, like hundreds of thousands of queries.
It's not like hours and hours and hours that it's going to be slower. It's going to be, hey, I want this like 100 concurrent users running a query, and these each seconds matter.
Okay.
So the Postgres gives a framework called GUCS. This is the Grand Unified Configuration, which allows users to control different parts of Postgres. Just let's ignore the vast majority and just focus on the optimizer parts. Those are of three broad categories. The operator GUCS, say, for example, you don't want index join, or you want index scan, or you don't want bitmap scan. You can enable or disable. Or you want to say, hey, I want to, or if I have a join order more than 20, for example, the Postgres planner will take forever to do join ordering. So I say the join order limit is 10 or 5. Or you just tweak the cost model to say, hey, I know the cost model is not perfect, so I'm going to tweak it for a little bit. But these are the broad categories. But what you need to know next is that these are hammers to the problem. So say, for example, if you have a large subquery and you want to specifically use one index, or some subtree you want to not use indexes, and some subtree of the query you want to use indexes. If you disable index scan, you will not get index scan for any of your subtrees. But that's like a hammer to the problem, right? So you want a means of have a scalpel where you can say, this subtree, I don't want you to put the index because I know there's computational skew, for example. Next. So PG hint plan is a framework that is well tested. It is based for Postgres optimizer or any Postgres-based solution, and many other competitors have used it. So what we wanted to do next is to take PG hint plan, which is an established extension for Postgres, and see how we can make it MPP for Greenplum. Next. So what we did is to make sure that now with the MPP solution for motions and redistribute and how those hints interact with a share nothing database like Greenplum, how does it do that? That's what we wanted to work on. So we have come up with a broad category of optimizer hints. One is the cardinality hints, which is how, say, for example, a customer is running a lot of inserts and updates during the day, and they don't want to do analyze because they need a scheduled time for doing analysis statistics. So what they do, usually customers run it in, say, every 6 hours. But within that 6 hours, your statistics may be wrong, right? So you may want to have a scalpel that says, during this time, I need this hint.
Venky, as a translation for people, cardinality basically means the prediction of how many rows will come out of something.
Correct.
Right?
SQL says select stock from foo, where stock ticker is avgo, because you're looking for Broadcom stocks and how they're doing. So say, for example, there's a lot of inserts on Broadcom stocks, then you want to know what's the selectivity of it, right? So you want to have a means in which of estimating the number of rows that would come out for a particular predicate.
Right, because if it's tons of rows, you're going to pick a different plan than if it's just a teeny tiny number of rows, right?
Correct. Correct. So, and usually what happens when you have like a banking system or a security system, you have a lot of inputs that comes in a very short period of time, right? A lot of ETL loads that come in, and you have to immediately start running real-time analytic queries on top of it. So you don't have time to analyze a billion inserts that come in, right? So you need to have a way in which, if there is a cardinality misestimation, you have a way in which you can get out of that problem. The second one is stable access hints.
Well,
So
one more thing,
basically,
thank you, on cardinality. So if, or on any of these really, if you have a scheduled job and you're happy with the plan and you want to make sure, for example, it's always having that estimation, that cardinality, you could kind of hard code it
yeah,
in the query so that the plan wouldn't flip flop, right?
correct, correct. So table access hint is same thing which I mentioned before about saying, hey, I want index scan here, I want a bitmap index scan here, or I don't want an index scan. So those kind of hints. Then the third one is join type. You can say, I don't want to do merge join. I want to do a hash join. So you can have those merge join type hints. The join order hints, you can specify exactly how you want the join order to be done. And the motion hints is how do you say, I don't want you to broadcast, and I don't want you to redistribute. I do want you to broadcast or redistribute the site. So those are the kinds of hints that we want to do. Next.
Okay.
A simple example for cardinality, you can set the number of rows, you can add the number of rows to the estimated cardinality, you can subtract it, or you can multiply it. So you can specify it in comment. So before the SQL, you have this comment section where you say the row estimation for this operation, please add, it is to be set to 42, or it should be added. Whatever you get, just add 42 to it, or subtract it, or multiply it. Next. In the same way, you can say for this query T1, I know you will want to pick an index scan, but don't do it. Use a sequence scan on T1. Or you could say, hey, I know you, if you please pick an index scan, and I have multiple indexes. Out of those indexes, please pick this index of mine. So you can specify which index also you use, because many customers have many. So say, for example, right, you have an index on AB, ABC, ABCD. So you have three options, right? Suppose your cardinality estimation is wrong and you land up picking the wrong index. So you don't want that. So you now have a way in which you can pick what index that you use. Next.
One thing, when you put this hint, for example, index scan my index, right? Is that going to be 100% of the time picked, or is that just an advisory saying lean
No,
heavy?
it's both Gux and hints are like firm saying to the engine saying, please do this. It's
Just
very
do it.
prescriptive.
It's not,
Just do
because
it.
I know in some of the other large database companies, they have hints that advise like weight it more, but it doesn't say do it. This is
Correct.
do
So there is no soft hints and hard hints. There's
yeah.
only a hard hints. But the only caveat is if you don't have an index and you made a mistake and created, say for example, when you created this hint in your job and then later on you dropped it, right? If there is no such thing, then it will not be a problem. But
So
if it is that index is there, it should be picking it.
so it's really not a hint, it's an instruction. Do it.
It's an instruction.
Okay. All right. Join type.
Same way, you can pick which join type that you want to do rather than say, for example, right? Many times what will happen is you pick a merge join over hash join. And sometimes hash join, if there's too many tuples, say, for example, hash join has a beautiful characteristic. When you have low cardinality for the hashing and very high cardinality of the hashing, it becomes very expensive. So there, the sweet spot where hash join works, and the sweet spot where merge join works. But all
So
of this is dependent on cardinality estimation.
you're saying basically small joins, nested loop is fast, medium hash is good, and merge is good for big things.
Merge is good when the data is sorted.
Okay.
Then you don't have to do sorting. So if there is a situation where you as a DBA, you as a user, you as an application developer knows that which hash join is better, because say for example, right, there are many jobs the customers have that are scheduled jobs that you want to have no change in behavior. You pin what you want and then say, hey, Orca or Postgres Planner, pick this. I know this is good.
Right.
And this is the way of doing it.
And join order.
Join order the same way. You can specify the exact join order that you want to choose.
Can you explain the difference between this one and this one?
So one is a left tree, like it's a one-sided tree. Other one is a bushy tree.
So is this saying like join T1 to T2 and then join that to T3?
T3. This one is saying join T1 to T3 join T2.
First join T3 T2 and then join T1.
Yeah, correct.
So you can be flexible like that.
Correct.
Okay. All right. Best practices.
So best practices of this is hints are to mitigate bad plan choices. Test your plan performance with the hints and figure out what the plan that you want. So because this is a tool to pin plans that you like. Periodically revisit hints because your data volume can change or data characteristics can change. And plan hints are temporary workarounds. So what we don't want users to do is to rely so heavily on plan hints that we are not getting feedback that when there should be actually some underpinning things that we can enhance, that we should make sure that you report any cases where it doesn't work as expected and you needed a plan hint.
One of my field engineers, whose name is Bert, I'll leave out his last name, said, please put bold and underline where it says periodically revisit the hints, because he said in other databases, if you just leave lots of hints over time, you could forget what you had and that could be a trouble.
Correct. And another thing is, one thing which we have to know, you have GUC. If you set a GUC that says disable index scan and you go around mucking around with hints, GUCs overseeds hints, right? So make sure the hints and the GUCs don't conflict with each other.
Right. So in summary, we now have hints. Hints are more exact and specific. They're in the code. They're not like global configuration variables, and it allows you to fine tune and advise what to do, right, from the plans.
In the query itself, you can have multiple subtrees having different hints.
And just to finish on this, I remember in 2009 or 10 having this discussion with our then head of R&D, and he said, we're not going to do hints because that says your optimizer is not perfect, and we're going to make a perfect optimizer. And to be fair, 14 years later, I think the goal of having a perfect optimizer is not realistic. And I think no database has a perfect optimizer. And that's why this whole concept of hints came out. Is that fair?
So yes, because the reason why there's no perfect optimizer is because optimizers rely on cardinality estimation. And then on top of that, you also have different hardwares that you're running, right? So all of the cost metrics that you're using to figure out whether this kind of index scan or this scan is better, with all these different varieties of hardwares that are coming in the market, which is ever changing because there's a lot of innovation happening, your cost metric is always going to be off. And cardinality estimation, the data correlation, between two tables, the joint correlation, all of those things, you can't model yourself out of that, right? The optimizer in a perfect world will be perfect, but the data is not perfect. There's skew. So and the hardware is changing.
So this empowers the DBA, it empowers the data engineer to control and fix the performance on their own. They don't have to bang at a black box that can't be changed. Right.
Correct.
All right, let's move on, Beth. So hints is new in 7.2. Congratulations on that. Let's talk about the improvements we've done for the Orca optimizer in 7.2.
So as Ivan mentioned in the first couple of slides, that we released Orca in 2015, and every year we have been improving the use cases that Orca handles. So what we have a wonderful situation in Greenplum is we have the next generation, the best optimizer for an MPP database, GP Orca. But whenever it's unable to generate a plan, we have an insurance plan, which is the Postgres-based optimizer. So what we are doing is not to chew the whole universe of all of the operators. So we chew about some percentage of it. So slowly we are adding more and more features, so we don't have to have a fallback to the Postgres-based panel. So the three which is coming out this release is the parameterized queries, support of full hash join, and distinct qualified window aggregates. Next.
That's great. So let's go through these three.
Parameterized queries is you write a function which takes in two values, and you have a select query inside the function. that uses those two values, this $1 and $2, which is the first parameter and second parameter. So this SQL inside the select query can be arbitrarily complex. It can have joins, aggregates, DMLs, functions, name it. All right. So what's happening is the user says, oh, for this table foo, run this function, some function with foo.a, foo.b. So at runtime, this function is populated with the values, and which in turn fires another query internally, right? That's a parameterized query. Next. So this could also be in a prepared statement. Say, for example, you say, hey, Orca, planner, generate a plan for this query, right? Fix the plan. I'm just going to change, say, for example, the stock ticker ID, right? I may change the stock ticker ID, but the rest of the things are going to be the same. So this is a prepared statement that is also a parameterized query. Next. So Orca now supports parameterized queries, right? So it internally treats this parameter as just a parameter that's going to be later on filled in, and it's just a constant expression. So there is no need for special handling. And it supports all cases, whether it's in the qual, projection list, limit, subqueries, etc. So we know in 7.2 onwards, we will not have any fallback that says feature not supported query parameters. The same thing is going to be also be supported in 6.28.
Very nice.
So the next one is the full hash join. So if you see here, there are two motions. The first sort motion, if currently in 7.1 supported merge join for full join. So it needed two motions. See the combination of sort, distribute, and again sort, redistribute below. These are two motions that needed. Or Orca generates another plan, which is a union between left join and anti-semi join. So you need two additional joins for just saying A full join B, right? So what we wanted to do next is to have a new operation which says, hey, I'm just going to redistribute the smaller side and hash it, and then have the sequential scan T1, which is the larger one, to probe the hash side. So we reduce the number of motions from 2 to 1, and we reduce the number of joins from 2 to 1. So this is a new feature that is added in 7.2, and it's also going to come out in 6.28.
So one thing people will ask, especially people who are medium technical, are going to say, how big of a performance gain would this give if you had this use case? Like if you had a 1 minute query before, does that make it like 58 seconds, or how big of a
it depends. It depends on how large is your join operation. If a join operation is very large, sorting is going to be having 10 to 100x improvement.
So theoretically, 100-second query in this case could be 1 second.
Correct.
Okay, that's good. Yeah, the optimizer is amazing how complex the use cases are, and but anyway, continue.
So the next small feature that we added in Orca this time is to have a distinct qualifier aggregate. So here, if you see, count distinct, but not with just regular aggregate. That was always supported, but with partition window aggregation. So if you see this over partition by, so we now support distinct qualified window aggregates in 7.2.
Okay.
Next.
Yeah, and I've definitely seen customers who use that. And by the way, do you want to mention? So basically, this just wouldn't run, and it would then fall back to the Postgres planner.
Correct.
Okay. All right. Let's go to AO tables. So AO are compressed tables, right? Optimized for data appending for big data. So let's talk about what's new and what's the current state in 7.1 and how did we improve AO and CO in 7.2?
Queries on AO and CO uses indexes when possible, but the current state in 7.1 is that the partial performance gain, because we only used to use bitmap index scan. So we couldn't use pure index scan with AO and CO table because of all of the random accesses, which could be suboptimal.
Right.
Right.
And if so, tell me if I'm wrong, but I think there's 3 types of scans in Greenplum or in generically, right? In these kind of databases, there's a sequential scan, which says go through everything.
Mm-hmm.
There's an index scan, which says go to the index and go one by one to what you're looking for.
Fetch that page and get it out. Yep.
So what is this middle thing, this bitmap index scan actually? Like this is halfway between, it seems like it's halfway between a sequential scan and an index scan.
So a bitmap index has a bitmap table that shows you which are the operators, which are the key. It's a key value store, right? And then you can go and fetch those particular values.
So I think the key point here is that when you switch to pure index scan, it's essentially the what the users intuitively think the index should be doing. So whereas
Correct.
we had on our compressed tables a bit of a workaround, and I think I recall the reason we had this workaround was because we couldn't accurately predict the cost when you had a compressed table of the different types of scans because the
Correct.
compression, different ratios, and it was hard, right? But now, did we change the cost model?
Yes, we did. We definitely changed the cost model.
So now that we
And
can,
so now we can actually it's distinguish like how many random accesses that you have to do for the index scan. So it'll cost it accurately. Therefore, we would say, hey, pick index scan here or pick bitmap index scan here. So
right?
we
So this,
have a couple of use cases where we now support where you will see the impact of this feature. The first one is let's look at this query. Select star from line item, order by some key, order key, limit 5, right? You want to have a sorted order of all of the line items and pick the top 5, right? So originally what we have to do is to scan the line item, sort it, and then do a local limit, and then gather it on the coordinator, and then do a global limit. That's how it would be working in 7.1.
and this in this case, this is even if you had an index, it would still do the, if I understand correctly, it would still
Correct,
scan the table and
correct,
sort the table because it
correct.
had to, right? So
Yep,
44.
and it took about 44 seconds. But now what happens is the beauty of index scan is sort preserving, it's order preserving, right? So now you can piggyback on the index, which you never used to before. Now say index already giving me a sort order. Therefore, all I have to do is to in each segment, I just have to pick the top 5 and then send it to the coordinator. The coordinator will then do a gather merge and then pick the global top 5. And this is about 1000x. It's from 44 seconds to 46 milliseconds.
Nice, nice. Okay, how
So
about the
again, keeping the same principle of sort order. So if you in PG vector we started supporting in 7, and we had to basically force like a gawk internally to say always if you see a PG vector query, always do X, right? But here, for example, we again use sort to do those PG vector issues because we didn't want to use the PG vector index because the cost model was off for AOCO tables.
so this is the similarity search, right? Where we're looking for example, it could be you have a text and you're looking for similar text in the vector format, right? And so it's an
Correct.
index search, but it still had to do a scan here, it looks like.
Correct.
Right. And now
Now
index,
what we have is, again, we use the index scan because the costing is done correctly. So we can use the sort order, it's preserved in the index scan, and then do a local and global limit.
okay, great. So this
And,
will help.
and mhm.
This
This is
helps,
about 100x faster. Yeah.
and it helps the AI related use cases too.
Correct. And just a caveat, right? The data set on these experiments are fairly small. Like imagine if you had like a 10 terabyte data set, right? It'll be like, it'll not be just 44 seconds to, what is it? Well, 44 milliseconds. It'll be from hours and hours to a couple of minutes.
Which brings me back to my key point, which is with big data, the optimizer is absolutely key because if you don't have a good query plan and you have a lot of data, you're going to be unusable, right?
Correct. And you have to use other technique of local caching or some middle tier, which needs more storage. So you are like not addressing the key problem by which you are having bad performance and just fixing all of the peripheral issues.
Right. Which is why after a decade, we're still saying optimizer, optimizer, optimizer. We need to continue to make best optimizer. You've got 3 more use cases here.
So I'm quickly going to run through this. Because we had in the optimizer hints, we had talked about merge join or group aggregates, where anytime when you need sorting, right? So now index scan already has sort in it. So group ag, which is like where you sort the input tuples and then you stream the aggregate non-blocking aggregate operator. Or if you want to do a merge join, the sort operation is instantaneous. It's free. So now you can use merge join when you couldn't do before. right?
Merge join
And
is
for
merge join is going to be awesome, right? Because you have two huge
correct.
tables with an index. The join is going to be like bang, right?
Super this join is going to be like you will get continuous results, right? Sort merge join, it gives you continuous group X, for example, it'll give you continuous results, not a blocking operator like a hash aggregate, right?
Right. Okay. All right.
And then the
Well,
last use case is
yeah.
point queries. If you have any point queries, this or index scan will be great. Next.
All right. So let's go on to geospatial topics. So let me introduce it and say that um, having a data type, or I think actually you're going to introduce it because now that I recall the slides, but let's go for it. You go ahead.
So spatial information, whether it is any of the door-to-door service apps or any of the like Uber, Lyft, many geospatial information, sensors, drones. So geospatial information is being stored more and more in real-time application, queried by real-time applications. So we need to have a way in which we can store them and query them in a most efficient way, especially if you have the scales of petabytes that you have stored in your data warehouse.
Right.
Next. So what we want to, let's take a simple example, right? This is a this is the open source New York, what is it, crime
It's
and
an open source data set.
open source New York data set, right? So one of the frequent queries in that is, hey, I want to find out every hospital that have more than 10 homicides victims who were brought in 2003 and that lived within the 2.5 kilometers radius away from the hospital, right? So
So
that's a
you're
simple query that we wanted to answer.
right. So you're combining, looks like you're combining two data sets, locations of one activity, locations of a building, and then comparing it with time and comparing it with distance.
Right, right.
Okay.
Next. So we have hospital data set and then you have the homicide data set, right? So all you have to do is to prune away in purple all the anything that's not a hospital from the buildings type. And then you prune away all of the 2003, that is only in 2000, you prune and you keep only the 2003 homicides. And then you group, you make sure you have that the building center and the homicide geolocation are within 2.5 kilometers. And then you say, I want to group by the building and and find out what are the counts that is greater than 10, right? That's a simple the way in which you will have right now with Greenplum and PostGIS.
And what's
What
the
are the
downside?
problems of this?
Yeah. What's the problem of this solution?
The problem of this, let's first see what it is good at next. It supports variety of use cases within interlap, overload, all of those intersection, everything. It's great. Like it has comprehensive functionality, it has index support with GIS. That's all great. But the shortcoming is because it's like you're talking about 2 points and how far away from they are, you don't know how they are distributed. You will have to broadcast everything to make sure to find the distance between every pair. So you can't do an efficient way of co-locating the tuples or some logical way of co-locating them.
You mean
Therefore the scale in which you're trying to query is not going to be supported by this
you're talking about for joining, right? Because you could if
or
you have
join it, because like homicides and this, see, so let's take a simple example, right? Any of those food services, app services, right? App deliveries who are going to match the person who's delivering the food with the restaurants, right? You have billions of that, right?
yeah,
You have billions of transactions happening, billions of drivers that are driving for these food services. How are you going to match them? Right? You're not
so
going to match it. Either you have like different geos having different data sets. That becomes very problematic. If you want to have a singular data warehouse that manages petabytes of data and query on top of it, this is the PostGIS solution alone is not going to scale.
now Venky, when I do a join on product ID, so let's say I have an order and I have a product table and they both have trillions of rows, right? And I join based on product ID, the orders and the products who equal the same product ID. I don't have this problem, right?
Correct. You don't
Why is
have this problem
why is this different?
because in product, the product and sales is a great example, right? If you distribute the product and sales based on the product ID, right? Whatever you're matching, you're joining on, then what happens is segment one has all of the co-location together, right? You could take even a simpler example, right? if you have hospitals and residents, right? If they're both in California, you can partition by California, distribution by state, right? You can distribute it by state. So all California is in one segment, Massachusetts is in one segment, all Kansas is in one segment. So any join between the state ID is going to be co-located.
So basically you're pre-dividing the data so you can just join
Correct.
the things with the same state or the same product.
Correct.
But why can't you
But
do that?
now, now you can't do this. Say, for example, it was great. Like, my kid was born in Kansas City, Missouri, right? In Kansas City, Missouri, and Kansas, they're adjacent to each other. So if you have an Uber driver or a Lyft driver who is in between, they can basically serve both cities which are on the border, right?
Yeah.
So you now have to figure out, if I'm an Uber driver or a Lyft driver who wants to do this restaurant pickup order, how am I going to do that? Like, how am I going to distribute myself? Because I have this 30-mile radius that I'm willing to travel to service my customers. How am I going to store all of the restaurants in such a way, wherever I am, I can go figure out what it is?
And if you don't co-distribute the data and you try and join it, then you're in big trouble, right?
Then you have to join with way more than, if not the worst case scenario, you have to touch everybody, right? Every restaurant you have to touch, right? So how do you solve this? So H3 is an open source hierarchical geospatial index. It was developed in Uber Labs, and that's what we're going to. It's an open source project which is established, and many other vendors or for different use cases are using it. But what we wanted to bring in is, how can I use H3 to solve the scale problem that we have in such queries? Next.
Would you use a hexagon and not just use like squares?
We're coming to that. So let's look at this H3, right? The first one partition is all roads. So all roads, where start and end, you have all of the buildings, right? Buildings are in this hex pattern. Then on top of that, you have all of the homicides, say, for example, within the dots that happened, right? And then you want to say, hey, this red box, that's the hospital epicenter. That's where the hospital is. I want to find out all of the homicides that happened within a particular radius, right? So say, for example, if that radius includes both the red hex box as well as the blue hex box, the only thing that I need to touch is these tuples. So imagine if I got to distribute whether it is homicides or buildings based out of these hex patterns. Then I need to only send this red hex box tuples to these blue hex box tuples, as well as the red hex box tuples, homicide buildings.
So
now,
if it's you're saying I want to find something within a mile, you look in this box, but then it might be like this one and this one are different box, right?
Yeah. So let's get into a little bit. There's a couple of more slides which explains a little bit the details of this. Okay, the first question is, why hex? Oh, when I was in computer science in undergrad, I always had a quad tree, which was all squares. And why not square? Why not a hex, right? Why a hex? The hex gives you a very important feature, right? That is, the centroid of a hex to the next centroid of the adjacent hex is consistent, right? The epicenter of these two hex are the same across, right? But that's not the case when it's a square or a triangle, right? That itself gives you a simple mathematical model for projection.
Gotcha. Right? That's cool.
Next. All right. So let's go next. So I'm this red dot, right? This is near Candlestick Park, if I'm not mistaken, and I'm trying to look for a cab, for example, right? So next. So imagine all of these hexes, right? Let's hypothetically say 1, 2, and 3 hex data are put on segment 1, right? And 4, 5, 6, 7 are put on segment 2, okay, right? And I know each segment is a 3-kilometer radius, right? Yep. All I have to do is to find out, and join only in segment 2.
Yep. Local
not
join.
Even. So for my rather than having 1, 2, 3 also be part when they're not going to meet it, I can skip them. Next. All right.
What is
So resolution, right? For each tuple, you can have various levels of resolutions. You can have as close as possible and to as far as possible, right? So this is and for each tuple, you can store the resolution, a resolution 1, 2, 3, 4, 5, 6, 7, and beyond. Next.
So I think I pulled this one from somewhere. So this shows the graph on the left shows there's 15 resolutions available in Greenplum for these hexes. And if you do resolution 1, then every hexagon is 234,000 miles. If you do resolution 7, every hexagon's like almost 2 miles. And at 7, the whole Earth fits 98 million hexes. So depending on what kind of problem you're doing, I guess you pick the resolution you want to use, right?
Right.
Okay.
So one thing which I want to, this is a funny thing. It always takes any established Greenplum user a small hash lookup to understand this. Is the H3 index is not an index in the traditional sense that Greenplum has, right? It's basically a mapping, like a hash map, like a mapping, not even a hash, like just a,
Is
each
it
hex has a particular number,
is it a data type?
right? It's a data type.
Okay, so
It's
H3
not an
index,
actual index. It's a
it's a
data type.
data type, and the data type is like, I think, is it like a integer? Kind of.
Correct.
It's a big
Correct.
integer, 64 or something. And then, so basically that index tells you does it tell you which hexagon you're in?
So we can get to that in a second. So
Right.
basically what I'm saying is for this building at resolution 7, I want, based on the centroid of the building, I want to come up with the H3 resolution 7 number, right?
So are you saying basically take this geometry point from a PostGIS table and
Mm-hmm.
get its centroid and then convert it in,
PostGIS function, correct.
right, and convert it to which index,
So
which,
you want to convert it into figuring out which H3 it will fall index for resolution 7. What is the hex it will fall?
which hexagon? Okay, gotcha.
Okay, and then you build an index on top of that. Can you go
Okay,
back?
sure.
So it's not an integer by the way. But what now I'm saying build me an index on top of this.
Right.
Right. Right. Next.
Yeah.
So you can say if you have the hex number, you can say, hey, for this hex, give me the top 5 or just any 5 buildings, right? If this is the New York State, New York data set. So this
So
is says I have.
it's a predicate filter saying, tell me all the
Correct.
buildings in this hexagon. Right? Yeah, he's
Correct.
coughing.
Right.
Okay. So now let's go into your
So
complex.
let's go back to the original query, right? I wanted to find the 2003 homicide. How do I do that? I'm going to say, hey, I want to find out from homicides, only keep the 2003 homicides, right? And then I say, I want to find out all of the grids that these 2003 homicides reside in.
Okay.
Right?
So you're going to
Okay,
first get the list of grids.
Correct. So then I'm going to say, hey, now that I have that, and now let me first prune the buildings which are only hospitals, and then I'm going to take that grid and then match it with the candidate grids of the other one.
Right.
Right.
And for the record, I always like breaking SQL down to multiple small queries. Theoretically, this could be done in a series of queries with temporary tables or.
Yes. So
Okay.
the first one, the H3 grid disk, because I needed 2.5 kilometers, I need, and that was like, so I needed not just the red hex, but also the blue hex.
Correct.
So I'm saying, give me the red hex as well as any adjacent blue hex. So I have all of those candidate hexes. Now,
So
all I have to do is my building in one of those.
correct.
Right?
But for me, as a more simple SQL, I could have said like just run this yellow query and store it in a temporary table. Right. And that gives me like
or
the
a
list
view, or a view.
That gives me the grid ID list, right? And then I want to combine that. Now we're doing fancy SQL, combine that with the hospitals whose centroid is in those grids.
Yep.
Okay.
And then you say, okay, now I have eliminated most of the things. now I have to become more exact, right? I still need exact location, right? So
Yeah,
I have exact location with 2.5 kilometers, and then next, and then use the aggregate more than 10 homicides. That's what I want.
right. Gotcha. Okay, awesome.
Next. Yep.
So what does this query
So
plan tell you?
so what we now have is, before we had to broadcast everything, right? We had to broadcast, and now we don't have to broadcast. We will have to just redistribute. That makes, because we have now distributed based on the hex,
Okay,
right?
so
We
that
have
means you're not,
distributed based on the hex.
so the distance, the actual distance query, the one that's checking like, are you 1.5 kilometers? It's not comparing everything to everything, right? It's now lesser comparison, right?
Who are you going to go join with? And you know where they are lying, right?
Correct.
Which segment?
Okay. And I assume this is the old way it was done,
Correct.
which
Mm-hmm.
is broadcast and compare everything to everything.
Yep.
So that
Yep.
so we've achieved what we call couples of orders of magnitude improvement.
Correct.
All right, let's go to, so that's the geospatial hexagons. I'm excited about 3D City. Let's talk
Do
about
you
that.
want to take that? Do you want to take that?
Hey, I'll do this one real quick. So 3D City is a standard data model, and there are people who generate this data and make it available. And what we've done is essentially imported this extension into Greenplum, so you can easily get access to these data sets that are available and allow you to do rich real world queries based on information about details of a city. So what's in these data sets, what's in this data model is stuff like about the buildings, about the streets and the railways, about the trees, about the lakes and the rivers, about the land use, the terrain, even things like benches, lampposts, traffic signs. Who knows what's in there depending on each city, right? And so you can poke into this data, upload this data into your system, and then start doing queries that leverage this kind of filters and these kind of attributes about what you're trying to analyze. So in this example query, just as a demonstration, we wanted to look in a specific city and see which buildings make good candidates to install solar panels. And so really it's just, I'm not going to walk through the query, but basically it's leveraging the information in the 3D City database or 3D City schema to identify which are the suitable rooftops based on the direction that they point and the size of the rooftop, and then filtering them out and using PostGIS and other geospatial filters to basically come back and say, okay, these are the good buildings, right? So we've gone from generic locations to information within the city that's rich information. I'm gonna bang through this part because, well, yeah. So that really brings us to the conclusion of the 7.2 features. I think we showed you the 7.0 features. There's like 50 capabilities in 7.0. This adds to it on 7.2.
And I'm super excited about 7.3 and 7.4 and beyond.
7.4 and beyond.
So
The before I'll just remind you, see the beginning of the video. We're going to now go into a unofficial forward-looking statement about what we're planning for the future. So see the legal disclaimer that plans may change in the future, but this is our current view of where we're going.
and some of them we are actively working on it. So let me jump into the query optimization, query processing, right? So right now for the index scan on AO tables, the cost model has been changed for the Postgres Planner, right? So we have to enable the same feature where we estimate the index scans properly for AO tables for Orca. So that's the one thing that is top in our list that we are actively working on. The second one with the parameterized queries, we have to have a better way of cardinality estimation. So, okay, great, Orca supports it, but we need to do a better way of estimating cardinality or doing better way of static partition elimination, right? So that is one thing we're going to be working on actively. We are expanding every version of Greenplum 7 and beyond will have multiple Orca use cases that will no longer fall back. For example, non-scalar subquery. So say, for example, if you say select star from foo, where a comma b, that means two values, equal to any select c comma d from bar, right? So you're comparing ab to cd. It's a non-scalar subquery. So that's what we're going to be supporting. We're going to be supporting lateral joins, aggregates with filter, and serve functions with volatile functions in the select class. So these are the list of functions that are query types that we're going to be supporting. Optimizer hints. As you may have noticed, I mentioned something about motion hints. We have not yet delivered on the motion hints. So we're going to be coming out with motion hints in 7.3 or 7.4, is how you can specify whether you want to redistribute something or broadcast some side of the plan, right? Just-in-time compilations, we are tuning the parameters. While just-in-time compilation is available on 7, we have to tune the parameters so that the customers don't have to personally tune it. So we are auto-tuning them. The last one is a very frequently asked feature where they want to have soft and hard limits for resource groups.
Let,
So
let me
say, for example,
let me clarify that one, Venky, because we already introduced soft and hard limits when it comes to CPU utilization. So I think what we're talking about here is soft and hard limits and concurrency.
correct.
Right.
So we have seen many customers sometimes shipping, like they're coming out with billion rows output. The amount of time it takes for the server, the client to absorb those billion row output takes a long time.
Even though the
And
query is
so
done.
even though the query is done, but the client is slow, who's absorbing the tuple. So how can I prevent that situation to happen?
Right. So one limit for queries that are actively running and another limit for queries, how many queries can be running that are in the final phase of delivering the data.
Correct.
Okay. More on geospatial?
More on geospatial. So now that we have H3 and you can redistribute on H3, which is awesome, what we wanted to do is to support functions that can tell you how can you balance your H3 such that your tuples are distributed and you don't have computational skew where one segment gets all of your data, right? So you will say, hey, I want resolution 7. But actually, if you distributed the tables by resolution 3, it would have been better. So you want to come up with user-defined, built-in functions that can help you aid in doing better distribution of spatial data.
Right.
All right. And then also changing the cost model so you can pick index joins better. So for like spatial index nested index nested loop. Index, and also you do index usage like just an SP just for these kind of spatial joins. Also another extension that we are going to be supporting is PG point cloud as well as PG routing. These are very popular extensions in the Postgres community. We want to support that in Greenplum.
In regards to PG Point Cloud, I know our deep sea oil drilling customers are interested in this because when they do deep sea oil drilling, they use LiDAR as the imaging technique, generates these very rich images from the LiDAR imaging, and those generate millions and billions of data points, which need a scalable platform to store and analyze that LiDAR data. So PG Point Cloud, I'm excited about. PG routing, I'll slightly, even though I still want to see that get finally done because there's some risk on that feature, making sure that we can make it massively parallel. But that's definitely very highly requested. All right, let's talk about machine learning.
Correct. So AI is hot, right? Everyone is using AI, ChatGPT, and many other avenues. So a customer, a Greenplum customer, right, or a database customer, they have different proficiency in machine learning or AI, right? So you could have a data scientist who's really Alice, who's great in any data science algorithms, but not familiar with SQL. And then SQL becomes the hurdle for them to use any kind of ML algorithms that are in database, right? So usually all of them come up, they write their own Python functions and they extract the data out of the database and run it through their Python jobs. So you don't like that is one case. Then you have Sam, who's the DBA, who's expert in writing SQL, but has very limited knowledge in data science, right? And they still want to say find out metrics and get value out of the data stored. Say, for example, if you're talking about hardware, right? When the hardware failures happens, then you have stored data. You want to predict when you have to change your disk or change something, right? They want to do those kind of minings. Then you have Eric, who's an application developer who has some bit of knowledge of both. They are comfortable in doing a little bit of both, but not particularly an expert of either, right? So what we wanted to do is many of these cases, where we say we want to guide the user through a set of questions so that they don't have to develop the ML queries, the SQL queries, or pick the ML algorithms, right? And so we want to have a bot that can help you through that process. And also, many times we have to tune these ML algorithms. They have different parameters that you have to tune to get the value that you want, right? So
Because
for DB scan,
the ML algorithms are a bit of a black box, right?
correct.
If you're a genius in statistics, you may have a sense that a SVM model will probably be very applicable to your data set. But I think the hidden dirty secret is until you actually train it and run it and see the output, nobody will really know which algorithm is going to work the best, or even what
Correct.
parameters to use.
Correct. So what we want to do is to have you want to generate the SQLs and maybe just a link to the PG cron, right? Maybe run these SQLs as a PG cron job at certain instances to test your thing, right? But you have to still generate the SQL that runs the ML algorithm inside the database, right? And then you want to store the models, you want to query the history of the models, and then you want to export. We have many customers who have multiple Greenplum instances that they train on the dev system and they want to export it to a production system or another system. Say for example, because of European data protection, they may have banks can have across different geos. So you have to export those models into different data centers. So how do you go to do that? Next. So what GPML bot does is it enables you to run multiple. It's a CLI based solution in the first couple of versions. And then we will develop a GUI based solution where you can run multiple models, right? And then that models after running will give you the ranks for the accuracy and the prediction of the different models and helps you pick the best algorithm that you need, right? And then once you train the models, you can predict the models. And once you predict the models, you can run it on different data sets and predict and forecast values, right? And then you can deploy them in a different system, right? You can deploy them in Greenplum, you can deploy them in Postgres. And in the future, we want to also deploy them in a Java application like Gemfire or Python. We have many customers, banking customers, credit card customers who use Gemfire and Greenplum together, right? Imagine like you have this data lake, Greenplum, which has all of this data, which you can train and predict, and then deploy it on Gemfire, which can detect credit card frauds at runtime, right?
Right.
So those are the examples we want to deploy against, right? So this
Cool.
is GPM bot. The first version is coming in the next couple of weeks. I think sometime in July or early August. That's our aim for the first version of the CLI is GPM bot, which will enable you to train, predict, and deploy it in Greenplum or Postgres. And in the future version, we'll have hyperparameterization as parameter setting, as well as Java-based application or Python application deployment.
Okay. So I'll take this one. So Greenplum streaming server, is the infrastructure we use to enable continual ETL. So traditionally, going back 10 or 20 years, ETL was a batch job. It was either a daily job, a monthly job, or hourly job. And there are some use cases still where you could do it daily or even monthly. But there's a lot of data sets that are continually coming in. And the goal is to have data in Greenplum updated in real time and to make the whole process of continual ETL more efficient. So Greenplum streaming server connects to Apache Kafka and also to Tanzu RabbitMQ, and it allows you to map a specific streaming topic into a specific table with transformations and have it continually updated in the database. So what's new that's coming in the near future for us is that we've taken our Greenplum streaming server, which has been out for about 4 or 5 years, and we've made it into a distributed framework so that it in itself can scale to billions and trillions of rows. So the idea is it's already there, it's already working great, but now we're making it more scalable and more highly available by having as many workers as you need. And we're going to be able to make these workers managed through stateless containers. So you've got stateless containers running these workers. You can have any number of them, and the state of what you've last loaded is stored in a transaction in Greenplum, based on the offset in the topic that you're reading from. So even if you restart all these streaming server workers, it'll just pick up from the database and say, okay, I left off this topic at this sequence ID and start continuing to stream the data. So this is really a, built for billion and trillion row streaming use cases that you can have, data updating every few seconds into Greenplum and continue to analyze and query with the latest, freshest data. I mean, while I got the mic, we're also working on transparent data encryption for Greenplum, which will enable the database itself to encrypt data when it stores it, and that'll help with some federal security use cases and things like that, some banking use cases where you don't want to rely on storage level encryption, but you want the database itself to transparently encrypt the data. And then as far as DR, I'm going to skip that slide, but the key point on DR is we're going to be introducing in the future versions of Greenplum read-only DR. So if you had, let's say, two data centers, let's say you had one in Paris and one in Frankfurt, and you're replicating the data to Frankfurt, and then in case you need it, you can fail over to the second data center. But since you've already allocated the hardware, you want to be able to use that. So it becomes a read-only copy that you can analyze the data and use it for a second-tier workload. So that's something that we're working on. And that covers the DR, but there's another use case, which is change data capture, which is more of a table-by-table replication, not a cluster or system-by-system replication. And this allows you to capture inserts, update, deletes in a table, and then replay them into another table in the same Greenplum and another Greenplum, or even potentially when you push it into JSON format, replaying it into an entirely another technology to have another data system that's capturing the changes as they're updated in real time. So this represents a kind of a whole flow of DR data protection features that we're working on in the Greenplum team. And I'll let Venky talk about the PXF work that we're doing.
Correct. So one thing which we have noticed with our customers is when they want to put a lot of archival data, a large amount of it in compressed Parquet format outside into S3, right? So this is that they have jobs that do this. That's very expensive. Some of them use petabytes of data that they are generating each day. So they want to offload some portion of it, which is all archival data, into S3 or some external Hadoop system where they can archive it, right? So for doing that, rather than consuming, while the main workload of millions of queries is still being firing on Greenplum. So currently, as it stands, PXF is going to be working simultaneously in the same segments where Greenplum is installed. So when you want to compress and do Parquet, so you have to order, you have to compress it, all of this are CPU intensive. So rather than having resource contentions within Greenplum itself, so customers can now have a PXF as an external system, which can run on Hadoop, which can run on other nodes, which is not having the same resource contentions as Greenplum has, and it can offload that work there where all of the sorting and compression can happen, and then putting it in the external source.
Right. Okay. Yeah. No. So this, I mean, my 2 cents, my take on this one is the building the data warehouse, the data lake together. Sometimes called a data lake house, right? It really gives us a scale out capability to go from hundreds of terabytes to potentially hundreds of petabytes, but really to be flexible between different tiers of storage. And so this is exciting. It's still coming in the future. We'll talk about it more when it gets released, but this is going to be good. So I think this was a long presentation. It was I don't know how many minutes this was. It was quite long. If you watched the whole thing, thanks for tuning in for the entire presentation. But we really wanted to show you how much work we're putting into Greenplum, how much work we put in, and how much we're planning to put in. We're really excited about 7.2, and we're really excited about what's to come, and proud of what Greenplum can do and where we're going with it. So thanks again. I'm gonna stop the recording and have a great day, everybody.